this is where we left off on the last movie. So we're talking about the concept of virtual condition. Okay, so we know perfect form is required in MMC per Rule 1 of GD&T. So in this particular case, our MMC is 1.260. That's the maximum size of this part. And then we have this straightness tolerance of 7 thousandths. So once we add the 7 thousandths to our MMC boundary, we get 1.267. That is our virtual condition. Think of it this way. If the part is made at its maximum size of 1.260, it's allowed to vary in straightness by 7 thousandths. Okay? What this does for us is that as the part deviates from its maximum material condition, it can handle more allowable tolerance and still fit within the virtual condition boundaries of 1.267. So that's what this next slide says. Virtual condition: when a geometric tolerance is applied at MMC, as in the previous slide, you get the shaft MMC of 1.26 plus the form tolerance of 7 equals the virtual condition of 1.267. So a part produced at MMC has a form tolerance equal to the value that's shown in the feature control frame. However, if the part is not made at its maximum material condition, if it varies below the maximum material condition, you actually get more tolerance. Okay, so at 2 thousandths below the maximum material condition of 1.258, we get 2 thousandths more tolerance. Okay, so straightness of the derived median line of a hole. Okay, so in this case we have a hole. It is a cylindrical feature, and we have a straightness tolerance on it. And in this case, it's applied to the feature of size. We know that because here's our size specification, and then here is our feature control frame of straightness for that hole. Or we put it on the other end of the dimension lines, and then it means the same thing. So a form tolerance is applied to an internal feature. So what does this mean? Okay, we have 750 plus 6, plus or minus 6. So the MMC would be 744, and then we have a tolerance of 5 thousandths, and that would be, we subtract that off, and we have a virtual condition of 739. So here is our perfect boundary here, virtual condition boundary of 739, and as long as our part falls within there, what we have is a MMC of 744, and then we have an allowance for the tolerance. Okay, such that if the part was produced above the MMC, we actually have more allowance for form. So again, this is another interpretation of virtual condition. So here we're going to talk about this functional gauging. Okay, so in which case here we have a drawing. It is a pin, and the pin has a MMC of 1.010 with a straightness of 5 thousandths. So what we can do is make a virtual gauge, virtual condition gauge, to check the functional. Okay, it's a functional gauge to check the virtual condition. So essentially our gauge here is a block which has a hole in it that's machined to the virtual condition, which is the MMC plus the 5,000 straightness tolerance. And as long as we could take our pin that's manufactured and slide through that hole, we know that the part meets the virtual condition. That's for a pin. Now in this case we got a hole. Okay, and again it's the hole the same as 1 inch plus or minus 10 thousandths with a straightness of 5. Okay, with that we create a virtual condition of 985. Okay, so to check this hole, size and form, we would make a gauge which is right at the 985, the virtual condition boundary, and as long as we could take this pin and put it through that hole, then we know that our part meets this size and form tolerance. Remember, size and form tolerances together are known as the virtual condition. So this is an introducing a concept of a functional gauge to check virtual condition. Okay, so let's talk about flatness of the surface. So, flatness specifies an allowable form variation for flat surfaces. Material condition modifier does not apply. The tolerance zone is bounded by two parallel planes. And here's how to apply the tolerance. You can do it with a leader, like this and this, or you can put an extension line and apply the tolerance to the extension line. So flatness. How to interpret a flatness tolerance. Okay, so what the flatness tolerance does, it gives us two parallel planes for a tolerance zone. And the min and the max surfaces of that part all have to fall in to the tolerance zone. Okay. So here it is at 3/1000ths max. All of our mins and maxes for all elements on that surface have to fall within this 3/1000ths max parallel planes. Now, how do we check that? We check it with a indicator and a height stand. And what we do is we run the indicator over the part and we check for full movement of the indicator. If the full movement of the indicator is less than or equal to 3/1000ths, then we know the part is good. It meets that condition. Here's where flatness is applied to a median plane. How do we know that happens? Okay, because we applied the flatness to the feature of size. Okay, so it's not applied to a surface like we did here. Okay, here we're applying the flatness to the surface. Here we're applying the flatness to the size. So when you apply the flatness tolerance to a size, you create this median, derived median plane here. Okay, so our tolerance zone becomes these 3/1000ths parallel planes that define the center of the part. Okay, let's talk about circularity. Only applies to control a surface form. No material condition modifiers are used. The tolerance zone between two concentric circles. So your tolerance zone is two concentric circles. Here's how to apply it. This is like circularity of a surface. You take your circularity and you apply it with a leader to the surface. And here's what it means. That if we took any of the elements along the length of that shaft and we were to spin them around, we would have something like this. We would have each element would have to fit within these two concentric circles. That's what circularity means. Now, cylindricity is an extension of circularity. It is a combination of circularity and straightness. So instead of your tolerance zone being two concentric circles, for cylindricity, your tolerance zone is now two concentric cylinders. And this is how it's applied. So there's your two concentric cylinders. Okay, I'm going to stop it here.